I'm aware that I'm the only person standing between you and your lunch, so I'll make it quick. Deep learning is a creation of machines which uses techniques inspired by the human brain's ability to learn. And until recently, we simply didn't have enough data or processing power to make machines learn. But now deep learning neural networks have many layers of abstraction. They range from simple concepts to complex ones. And that's what puts the deep in the deep learning. And it has countless applications ranging from medical diagnosis, surveillance, robotics and automotive safety, and other computer vision applications to speech and text recognition. Speaking of which, voice recognition technology, we know, could revolutionize the way we interact with machines. But currently, the available systems are expensive and proprietary. Common Voice is a project to make voice recognition technology easily accessible to everyone. And people can donate their voices to a massive database that will let everyone quickly access and easily train voice-enabled apps. And it's available for all the data will be available to all the developers and everyone who can access. And production quality speech-to-text is currently a domain of a handful of companies that have invested heavily in their research and development. And to access proprietary speech-to-text services, a common man will have to pay in the range of cent per utterance, which is a huge cost. Mozilla plans to open source its speech-to-text engine. So this is a great step. Slowly these days, the data has always been a problem before, but nowadays the data is being accessible. Companies like Mozilla are open sourcing the models and the data. But coming back to the topic, real-time object detection. So what is object detection? Even before that, what is the difference between image classification and object detection? So image classification or recognition is the process of taking an image as an input and outputting a class label out of a set of classes. And the input is an image, and the output is a class label to which it belongs. It checks whether or not the object exists, yes or no. Image classification with localization takes an image as an input and outputs a class label and also draws a bounding box around it. So basically, it locates the object within the image. The input is an image, the output is a class label, and a bounding box. So with localization, we also know the location of the object within the image. Now in object detection, image localization has to be applied on all the objects in the image, which results in multiple bounding boxes. So the input is the image, the output is the class labels, and the bounding boxes for all the objects in the image. The objects identified can belong to multiple classes. So basically, it's not just if the object is there or not. It's if it's there in the image and its relation to other objects in the image, whether we can draw bounding boxes around it, whether we can partially see it, and whether it's covered and we can still see it, or something like that. So object detection has plenty of applications like self-driving cars, face detection, pedestrian detection, in security, automating checkouts in stores like Amazon Go, and a lot more, or simply just detecting The Simpsons. So before talking about a particular algorithm, a quick primer on convolutional neural networks. So convolutional neural networks have a different architecture than regular neural networks. Regular neural networks transform an input by putting it through a series of hidden layers. And every layer is made up of a set of neurons, and each of them is connected to all of the neurons in the previous layer. And then there is a fully connected layer, the output layer, and that represents the predictions. Convolutional neural networks are a bit different. And first of all, the layers are organized in 3 dimensions. They have height, depth, and width. And the neurons in one layer do not connect to all the neurons in the next layer, but only to a small region of it. And the final output will be reduced to a single vector of probability scores organized along the depth dimension. So basically, they have two primary components. The hidden layers, the feature extraction part that is, in this part, the network will perform a series of convolutions. So basically, the name convolutional neural network is because the primary operation is a convolution. So there are convolutions and pooling operations in which features are automatically detected. So if you have a picture of zebra, there will be features like the stripes, etc. And each layer of a convolutional neural network identifies some features, and they get more complex as the layers advance. So in the first layer, maybe it's detecting a black patch, then maybe black surrounded by white in a body shape like that, and then maybe facial features of a zebra, things like that. It keeps getting more complex. And the second part is the classification part. So here the fully connected layer serves as a classifier on top of the features extracted, and they'll assign a probability for the object on the image for being what the object algorithm predicts it is. Now, YOLO, you only look once. So before even that, going by the standard approach, if you use a convolutional neural network, to detect images, what we can do is repurpose a convolutional neural network. We can have a convolutional neural network and slide it across an image. We can divide the image into 12 by 12 pixels and slide it, continuously keep classifying each and every grid, and we can detect what object is there in that part of the grid, and we can continuously do that for the whole image. But that is, we can actually get a bunch of different bounding boxes, and then we can maybe filter them out by which ones we want, depending on the threshold. But that is still a very brute forcey approach and very computationally expensive. So better methods were invented. Region proposal based methods were the ones that gave region proposals before actually doing the classification. So they used some particular algorithms which suggested some regions. For example, selective search was one of the algorithms. And then after the regions, only on those regions the classification was performed. But even they were not so fast. I mean, they were accurate, but not fast, not good for real-time systems. So YOLO was a one-shot object detection algorithm that they developed, and it is the fastest one that exists. It is a very good choice when you need real-time detection without loss of too much accuracy. They have released the third version very recently in March. But in simple terms, it takes a very completely different approach. The first version of YOLO, what it does, it divides the image into a grid, and each of the cells is then responsible for creating some bounding boxes. The bounding boxes describe the rectangle that encloses the object, and then YOLO gives a confidence score that the predicted bounding boxes actually contain some object. For each bounding box, a class is also predicted. Out of so many boxes, most of them are going to have low confidence scores, so we only keep the one above a certain threshold. So basically the key of all this is that all of these bounding box predictions, everything is happening in one go, once. Actually, you serve the image only once to the deep learning system. You only look once. And so basically, this is the first version in very simple terms. Second one had some major design changes, and the third one, which is released recently, also had some design changes and improvements, and it's much faster. But let's look at how we can, so basically it is also very fast. So it is 3.8 times faster than RetinaNet. RetinaNet was released recently and was supposed to be the most accurate one-shot learning, deep real-time object detection algorithm, but it is still very slow. So YOLO version 3 matches up the performance as well as the accuracy. So let's check the implementation. So first of all, we're gonna use, all right. So YOLO was originally written in Darknet, which is a custom deep learning framework written in C and CUDA by the authors, and it's great and super fast. But since there were a lot of Pythonistas and C is not very user-friendly, there was a Python version implemented. So that's called Darkflow. That's a port of Darknet called Darkflow. So now what we're going to do is use the command line utility that they provide. Before using in our Python application, we're just going to experiment with the command line utility. So it needs Python 3.5 or 3.6. We're going to use TensorFlow. If you have an NVIDIA GPU that's capable of running TensorFlow GPU, that's recommended. But if you don't, that's not an issue. It'll be a bit slow, but you can just use TensorFlow for CPU. That's just pip install TensorFlow. And once that's done, you will need OpenCV, and the next step is to build the library. So once you do that, there'll be a build folder, something like this. This one, it'll be there. It'll be automatically created. So, yeah. Once we've built the file, so everything is built now, we're ready, we can proceed. Once we build the file, the next thing we need to do is download the weights for the model. So when we use any deep learning algorithm, there are two ways to go about it. Either you can just train the algorithm from scratch with your huge data set, labeled data set, and then test it on new objects or whatever you want to do. That might take days. Or else you can download pre-trained weights which have been trained by someone else and published online. So that's an easier method. We're going to go with that method. So there is this website these people have built, and they've published the weights of all the algorithms, YOLO, version 3, version 2, SSD, and other alternatives. So you just download the weights and move it in the bin folder. So we create a folder called bin, and then we're going to do is we take the downloaded weights and put them inside. And we're all set. We can render some video and add bounding boxes and labels. So I'm going to show you how to do that. I've just recorded outside this room a video. So if I go to my folder, I have this video called, so video.mp4 is the one I've recorded. And it's currently just raw footage, unprocessed. What I'm going to do is use, so this is the command that we need to use. We can open up a command line window. We can write this command by calling flow and specifying the model location. And we also need to specify the pre-trained weights, the one we just downloaded. And what demo does is we provide a path to a video file that it's going to process. So in this case, I named a video file just video.mp4. And if yours is named something else, you can use that. If you don't have a GPU, you can just skip the GPU part and skip it off. And save video just saves the video. So when I do that, I run the command, and it starts processing. So it lists down the architecture of the network. It's running entirely on GPU, and then it starts rendering. So currently it's very slow because I'm running it entirely on CPU, and also it's the YOLO version 2 because YOLO version 3 is not yet compatible with Darkflow yet. I can use directly darknet, but the port for Python is not compatible. So I already have this processed. It's going to look something like this. So it's detecting that that's a person, that's a table, so it has processed the video, and some things are happening. So this is how we use the command line utility. Now coming back, yes, it's something like this. So now we want to process images and videos in our own Python application ourselves. We want to add bounding boxes and labels and use it in our own Python application for whatsoever reason. So starting with the imports, now what I'm going to do is define options for running a model. So we're going to create a dictionary called options, and it's going to specify the models, the weights, the thresholds, and if you're going to use the GPU or not, just like we specified in the command line right now. So it'll be a dictionary called options, and threshold is how much or how good a confidence factor it needs to have in order to draw the bounding box. So we're going to define a threshold of 0.3. What this means is it needs to have a confidence probability greater than 0.3 in order for it to show up in our image. If we set it too low, then there's going to be a ton of boxes and it's going to be cluttered. So we don't want it to set too low. So 0.3 should work fine. And that's it for options. So if we create we also create an object called tfnet, and that's the one we imported. That's from the Darkflow library. And we're going to pass the options. So if you try to run this part, I have here a Jupyter notebook, and these are the options that I've specified. And if we try to, all right, I have specified YOLO v3. I'll just modify it to tiny YOLO VOC, which is the YOLO version 2 trained on the VOC data set. So similarly, it lists the architecture and yeah. So now we can go ahead and yeah. So it displayed the model we are using. We're ready to process the image. So I have clicked a picture. I have downloaded a picture from the conference where people are standing in a line, and I'm going to try to process and detect things in it. So what we're going to do first is create an object called image, and we're going to use OpenCV. So we pass the image, and we're going to try and predict what's in the image. So if I actually try to do that, in my Jupyter notebook, I have here, I've passed the image that I downloaded, and if I check the result, for which I'm using the return predict function, which this actually gives the result by the algorithm. So it's detecting the bottom right, the confidence. There are multiple people in the image, so I have multiple objects. All these are the coordinates of each object in the image. Bottom right, confidence level, how confident it is about the object, the label, so it looks like there are only people in the image. So yeah. So now we're going to use these results to draw a box and display a label on the image. So this was the output by the algorithm. Now we're going to use OpenCV to just visually draw some boxes and bounding labels using these coordinates. So if I create a top left, and it's going to be like, so it's a list inside the list. So it's basically all syntactical. Here I have written 0 because it's only one element. If I have more than one element, I'll have to loop over all the elements. So I can take top left, and I can take the bottom right, and I can take the label from the dictionary that is being created. And we do the same thing for the bottom right. And using OpenCV commands, we're going to draw a rectangle on the image by passing it and the coordinates and the color and the thickness of the box. So once we've done that, we can also use matplotlib to display our image and the bounding boxes. So we're going to add the label. In order to do that, we'll redefine our image. It's going to be cv2.put text. It's all basically syntactical. You can check the syntax to put a rectangle, put a text. We're going to pass the font size, color, width. And if we do that, so after I run this, it's showing me people standing in a queue, and it's detecting that there are some things. If I remove this command, it's going to show me what over this. I don't know if you can see it, but it's written person. Yeah. So basically, it's written person over each bounding box. The label is the person that is being detected by the algorithm. All right. So moving on. So this is done for images. Now we have labels and bounding boxes for images. Yeah. So if you want to do the same for videos, what we'll do differently now is we're going to create an object called capture, and it's going to be cv2.video capture, and then we pass the video that we want to process. And then I just want a random colors, just some variation to the boxes. And while our video is open, we're gonna do this. So rit is gonna be either true or false, like it's true when the video is playing and false when the video ends. And frame is the actual frame. So now we're gonna create the result and return predict like before, which is gonna pass the frame. And we zip the colors and results, so one color, one result. And most of the things, basically the summary of all this is most of the things are similar to the previous step. What we do basically in this step is take each frame and pass it to the algorithm as we were doing for images. So we loop over each frame of the video. So if I try to run all that, this is. So I'm running one virtual reality video that I have. So you can see it's detecting in real time. This is a TV monitor, this is a person, and frame by frame it is happening in real time. It is actually processing right now in real time. So, all right. So that's all for the video. And now one last thing, if we can try, is that we can do all this with a footage being taken directly from the webcam. So I have a very low quality webcam in my laptop right now, but yeah, I think it'll do just fine. So almost everything is going to stay similar as the previous video, except a very few things. So we're gonna create a capture object just like before, and we're gonna pass it 0, so I have only one webcam, so 0 is gonna be fine. If you have more than one, then the number might change. And so I'm gonna define I'm gonna change the height and width, so we're gonna use the full 1080p frame size. So if we're going to, so now let's proceed to our while loop. And it's going to look pretty much the same as before. We're going to be reading from the capture device, and we'll do capture.read. If this is not visible, I'm going to be sharing the slides, so that's not an issue. We're gonna check if capture device is still going on recording. We're gonna do a prediction. We're gonna add a boxes to the frame. And we're gonna do the for loop where we loop over all the prediction, and similar to the steps we did before. So I'm going to try to run that. So this is where I set the capture device, and then I start the video. Okay, not quite. Okay, so this is me being detected as a person. So yeah, it works in real time too. Great. So yeah, so that's pretty much all so basically the rationale behind calling the system YOLO is that passing in multiple, we pass in multiple, rather than passing in multiple sub-images of potential objects, you only pass the whole image to the deep learning system once. And then you'll get all the bounding boxes as well as the object category classification in one go. And that's the fundamental design decision of YOLO. And it is what makes it a refreshing new perspective on the task of object detection. And the main selling point of YOLO is its promise of good performance in object detection at real-time speeds. And that allows its use in systems like robots, self-driving cars, and drones, where being time critical is very important. So basically, YOLO has demonstrated significant performance gains while running at real-time performance. And that's important right now in the era where there are a lot of resource-hungry deep learning algorithms. And as we march on towards a more automation-based, automation-ready future, systems like YOLO will be the key factors in determining the big dream of artificial intelligence. So yeah, that's pretty much all I had to share. It was a small demo, but all these are open source algorithms. These days it's becoming more and more accessible. So you can check out the GitHub repo, you can send pull requests, you can use it, you can modify them, or you can do things. So yeah, if there are questions, let me know. Thank you.